we start on we will talk about what a sheaf is and specifically the kind of sheaves that we'll be using. There's a vast literature of sheaves out there. There's books and books on sheaf theory. None need to know all of them. The kind of sheaves that for now we'll be studying and the ones that for now are in the literature in relation to Legendre submanifolds are very, very specific sheaves. They're like sheaves that if you talk to an actual sheaf theorist or something, they'll be like easy. Okay. So yeah, like don't be daunted by the fact that sheaf theory is a really vast thing. So the quick disclaimers are there in the board. So in the notes, I use general coefficients. You can absolutely ask me, why would you want to do that? There's a point to this, but in these lectures, the general coefficients are always going to be the digit-derived category of modules over a certain unital ring, commutative ring. Just think vector spaces if those words like are not okay with you. Now, category, I will purposefully be vague about it. The notes are precise with the references, but when I say category, it will either always mean a digit-derived category or an infinity category in the sense of a quasi-category. There's advantages to using either approach. I do not know one approach that takes advantages of both and doesn't have the disadvantages. And finally, every time I'll talk about sections, morphisms, and everything, it's implicitly derived. So I'm not even gonna like add the word R or anything. It's just more stuff. Okay, so where were we? We were in T star of R2. And remember that we had this projection down to the 0 section, R2, coordinates Q1 and Q2. And the idea here was that in here we're going to have our Lagrangians. So here we're going to have our Lagrangian fillings, Lagrangians. And think of them as having boundary, some specified lambda in the infinity boundary. So Lagrangians L with partial of L equals lambda. And here is where we draw fronts. So here you had like fronts for lambda, which this specific boundary, as we saw in that theorem, you can manipulate, you can do Legendre isotopies, and thinking of them in terms of movies, you can find Lagrangian fillings in that way. Okay, so in this situation, the sheaves are happening here. So this is where the sheaves are happening. Sheaves. In general, for a T star M, the sheaves happen on M. And for a more general Weinstein manifold, the sheaves happen on the skeleton. So this is where we're going to do sheaves, and we're going to talk about categories and sheaves of sheaves in R2, and then we're going to connect to this cotangent bundle with a very specific notion, that of the singular support. Okay, so first of all, what is a sheaf? So definition, first construction, is you consider a functor, I'll boil it down to details, so we'll consider a functor F from the category of open subsets in general for some analytic manifold M, but that's some manifold, in this case R2, into sort of coefficient categories. So in this case, coefficient categories, I said, I'm going to take it to be mod K. So in general, you would say, you'll talk about sheaves or certain functors from this category to some other category. Let's say vector spaces are a target just to begin with. So what is this category? It is a category that has its objects are open sets. So the objects are open sets. And morphisms are inclusions. So the ohms are inclusions. So U inside of V as an inclusion of open sets. So what is a functor? Well, the data is for every open set here, for every object U, I gotta assign to you an object of this category, the coefficients, sheaves per point if you wish, which in this case will be a vector space. And as I said, everything is derived, so every time I say vector space, I mean a complex of vector spaces. Okay, so that's the first thing, sends objects to objects. Now it has to send morphisms to morphisms. So every time I have an inclusion, U inside of V, I should assign to that inclusion some map, let's call it rho of VU, that goes from whatever I've assigned to V to whatever I've assigned to U. Okay? If you want contravariant or you want me to put an op here, that's fine. Okay? So first of all, a sheaf is a functor of this kind such that it satisfies certain properties. Okay? But first of all, this is the data that we are given. It's sometimes called a pre-sheaf, which for every open set we assign something, and for any kind of inclusions, you're going to have something there. Again, we're going to be focusing very, very severely in our R2. So our sheaves, I'm always going to draw as if the blackboard was our R2 in here. that's Q1, Q2. And so, for instance, you have an open set here, U. In general, I'll try to adopt a convention for now that the lecture notes do this, that if I dot the boundary like that, that means it's open. And if I don't dot it, like if it's a continuous thing, then it means it's closed. Okay, so that will be something in here, and then maybe you have something color coded right now. So this is U in here, V is in here, and maybe you assign some vector space in here, some vector space in here, and then you have a restriction map, which is going to tell you how to map the vector space on the larger one to the vector space on the smaller one. And that restriction map could be anything in life. It could be the zero map, it could be an isomorphism, it could be injective, surjective, it depends. It depends on what you assign things, and the richness of shift theory is in all these choices. Okay. Now, if you just study functors this way, no restriction whatsoever, things get kind of out of control in the sense that there's not that much that you can say. And rather, what happens in nature is that when you're studying things of that sort, you might want to start thinking about gluing, as to have an open set and another open set, and maybe they overlap, and maybe I have some section here, another set. By the way, these are called sections. These are called sections. Because a typical example of such a functor is sections of some vector bundle. So now you start to glue together, and you would like that these local gluings somewhat reflect something global. That this kind of thing is interesting. So in order, I'm going to continue here. So in order to capture the notion of local to global, so the local to global principle, we're going to introduce a certain complex / diagram, which I'm going to denote like that. By the way, this is going to be a very non-traditional way of talking about shifts, but I just find it to be clearer to me. So every time I have a shift, you can consider the following thing. So for any open set U, so this is an open set. Now you take an open cover for it. So take U sub I, an open cover. So this is an open set, and this is an open cover. Sometimes we will denote this by saying that U is of the form of a bunch of UIs, just means it's U, okay? So for instance, you want to cover this guy in blue in here, and now so it's U, and now you start having one U1 in here, another U2 in here, another U3 somewhere, so on and so forth, okay? That's just an open cover. To capture the local to global, so this piece would be the local, the little guys are the local, these guys would be the global. If you want to do it on the whole manifold, we'll take U to be N, the open manifold, clearly. So to any such open cover, you can introduce the following diagram. So for any such open cover, given this data, consider the following operations. So the first thing you do is you take local sections on all of these people. So for each of the UIs, you take whatever the whatever the functor is assigning to them. Okay, so whatever. Okay. Now you want to do this for all of them, so you take the direct sum. If you have any, that means finally. Now each of them, using the restriction functors, will have a map. So U1, for instance, will have a map to anything which is U1 intersected with something else, because it's going to be inside of U1. So let me just very quickly denote UIJ to mean the intersection of UI UJ, UIJK to denote the intersection of, so this would be UIJ intersect UK, so on and so forth. This to this notation. So each of these guys is going to map to UIJ for any J, and it does so in two different ways. So let's think about it for a second. So if I have here f of U1, think of, yeah, Uncle?
Anything people change the markers or something?
Is it bad?
It's very hard to see.
Which one?
The red one, this one.
The red one is the bad one.
Use the other red one on the board. I think that might be better.
Most important diagram. So is it better? Yeah. All right. So let's do an example with three covers. If you had U1, U2, U3, well, U1 and U2 intersect in here. Let's make U3 intersect U1 in some interesting way. So you have intersection from U1 to U1, U2 in here, U1, U2, and you also have intersection of U1 with U1, 3. Okay, so every such guy maps to two people in now. Okay, to the double intersection. And this gets iterated. So every double intersection now maps in three ways to the sum of the triple intersections. F, UI, JK, so on and so forth. And this diagram continues getting more and more and more arrows. All right. Let's call this diagram the check diagram. So this is a very important diagram that I'm going to use in two different ways. It's called check diagram. And for now, I'm thinking of it as a diagram. Okay. So that's what it is. And what it's trying to do is to capture all these local things and the possible ways in which they match or not match together. So for instance, if I have a section here for U1 and a section here for U2, the fact that they coincide in here is the fact that under this map, this thing goes to 0. So on so on. So in general, you can do that for any such functor f. But the problem is, it might be that what you want to compute is sections on this whole U, and you're trying to use all these local sections glued together in all these ways. And in general, for many interesting functors, it does not happen that this diagram captures exactly f of u. That's exactly the definition of a sheaf. So let me write here the definition of a sheaf. So f is a sheaf if the natural map from f of u to the limit of this diagram, natural map from f of u to the limit of the diagram, which I'm writing in red. This is a check diagram. Let's try it like that. Limit of C, U, UI, F. So I'm going to be calling this check diagram. Denoting C, U, UI, F. This understood this. So if this map is an isomorphic. So okay, so first of all, well, why is there such map and what is it telling you if it's an isomorphism? Well, first of all, because each UI is inside of U, it means that there's a map from FU to any of the FUIs, right? So there is a map from FU to any of the UIs by restriction, and then therefore there's a map to the direct sum. So there's a map to this first term, and actually, because everything goes to the right, there's a map to the whole diagram. Okay, but now the condition is that this as a diagram, you want the limit to be exactly f of u. So let me do the example that mostly we're going to care about during these lectures. So example in here. And if you don't have an infinity category, you actually have an honest category in the classical sense. This is what happens in general. You don't have to worry about it. What you're saying is that f of u maps into the equalizer of the first two maps. So this guy. So f of u is mapping into the limit of f views and then the double intersections. And that's probably what you might have seen if you take a book in sheaf theory I don't know, pre-2000, let's say pre-2000. Like the classical series of Bredon and company, Godeman, the sheaf definition is exactly this. It's exactly the definition is that this f of u is exactly this limit in there. What does the limit mean? So in this case, this is an equalizer. So here I have two maps. So the limit of these are exactly going to be people from here such that under these two maps, they go to the same thing. So these are exactly people from U1, say U2, that map exactly the same, meaning they coincide in the intersection. So this guy being an isomorphism, that statement is equivalent to two conditions. So this is equivalent to, usually it's written in two conditions. Number one, sections that coincide in intersections glue. And the second condition is they do so in a unique way. So sections that coincide in intersection, the double intersections in this case, do glue, meaning there exists, if I give you a section over here and a section over here, if they both coincide in here, then there's a section on this whole area. And then the second statement is you do so uniquely. That's the objective part of this. There's a unique section that's determined by this data. Do so uniquely, and then these two things together is this condition here. So you say, again, this is a good definition at the beginning of today, is F is a sheaf. If it satisfies that this map is an isomorphism, so that will be a condition. Here, this is an isomorphism. And classically, you can truncate for one categories to something like that, which is your classical definition. I don't like the classical definition. This sounds extremely more natural to me. Why would you stop after two? That always annoyed me as a grad student. The reason is you shouldn't stop. You should consider the whole thing, and if you have infinity coefficients, that's the thing to do. All right. Any questions so far on sheaves? On like this definition?
You have what, if you have what, coefficients, that's the thing.
So if in here I had something that's not just a category, but an infinity category, something like I just have compositions, but I also have commodities between the commodities, then the definition of a sheaf is this one. And that doesn't make sense. Like this limit is not the same as this limit. So when you have infinity coefficients, you need the whole complex. I mean, it's like for topologies, why would you tell them like, oh, only build spaces using vertices, edges, and faces, like never use three cells? Well, of course you can use three cells. Wait, Lenny?
Is there a good example to keep in mind for the difference between this definition of sheaf and the classical one?
Wait. You mean an example for like the,
Something that's a sheaf in one sense, but not the other.
well, I think the short version is almost anything that's, if you have infinity coefficients, anything that's gonna be a sheaf in this sense is not gonna be a sheaf in this sense. I mean, it just doesn't, it's like the T0 truncation, like it's not gonna preserve the property. Okay, again, that as a comment. Okay, so let's start thinking about some examples and let's make your lives easier when you do examples, right? So first of all, you can always choose the constant functor. So you just choose exactly this functor to send every open set to the same vector space. And you might as well choose the morphisms to be sent to the identity of that vector space. That's called the constant sheaf. So whenever you specify an object of this category, say a vector space, for instance, K, that gives you a sheaf, which is the constant sheaves.
I guess if you use this, this definition of sheaves, then maybe the constant sheaf should be taking any open set to the cohomology of that open set.
Yeah, well,
And this, in particular, gives an example of what's the classical definition, when the classical definition is not the same as the.
yeah, I'll get to that in a second.
Okay.
I'll get to that. Yeah. Okay, okay, well, so there's this sheaf in here, because then I need to change the scale. Slide, but, okay, so that's one example. Another example would be sheaves of, for instance, continuous functions, sheaves of smooth functions. So for every open set, you consider all smooth functions on that open set. These sheaves are at the two extremes. So the constant sheaf, it's going to give you the anti-Legendrian, and the sheaf of smooth functions is going to give you the entire cotangent bundle or the entire infinity of R2. So that's going to be an example of something that's not a Legendrian, it's quasi-tropic. So the sheaves that we'll be studying will be somewhere in between. They're not going to be as wild as the sheaf of smooth functions, but they're going to be slightly more interesting than the constant sheaf. Yeah? All right. Any other questions on this? Yeah.
Is there a reason why, reason that we use the direct sum not product?
Let me answer that later. In our examples, no, there's no reason. But for other settings in shift theory, not in the analytic setting, I think the answer is yes, there's a reason. But it's not going to affect us. For sure.
So you should use product if you are defining a sheaf, but if you are defining a co-sheaf, you use direct sum.
Okay, you're saying I should have used products in here? I'm happy to switch to products. None of the examples is going to make any difference.
You are saying yes.
Yeah, so okay,
Sorry.
put products everywhere. Like all stratifications here are going to be finite, which implies that all these products are going to be finite in all our examples. All right, so now we maybe have a definition of a sheaf somewhere. Now, an important notion is the notion of the sections of a sheaf. So let me just use the second definition. And then we'll do a bunch of examples. So give the sheaf. F. And typically we're going to denote a sheaf in a manifold, in this case, it's gonna be R2 by these letters, sheaves in R2. Just means those functors from the category of open set that satisfy this condition. In the sheaves, it's derived global sections, which we'll just call it global sections. Are, and then I'm pretty kind of cheap, but so I'm still gonna denote it gamma of F. Sometimes it's also denoted by indicating the space. So you would say gamma of R2 F is, so this is defined to be this complex, but now understood as a complex. So first I was using this as a diagram, and therefore it has a limit, and I was using that limit. Now I'm using this as a complex. So there's a non-trivial statement is that this is a complex. So this I'm using here. I guess that's right. Global sections. It's global sections on U, an open set U, are given by this complex. Okay, so again, classically, if you're thinking homology or things like that, you would take the homology of that. That's fine by me. If you know the whole thing about how to take derived functors, that's where these things are coming from. But this is what's classically known in the literature as check complex. So you can check, no pun intended, that this is a complex. And
Are you making some choice of covering UI?
yeah. So on U, always. And then this is for a good cover. In practice, you're always going to use good covers for these things. So I know I'm differing from, okay, so option one is I spend hours talking about sort of, there's enough injectives, there's resolutions, there's left thing. I can do that if you want, but in practice, nobody uses that to compute anything. You use check complexes. So might as well just say, this is what check complex is. Just like do that, and then say, if UI is a good enough cover, which you'll find this is independent of the cover. Okay, so this will be independent of U, so independent. If under this hypothesis. Okay, so this is our definition of global sections. And at the beginning, so a quick remark is at the very basic level, the first step, this recovers F of U has the zeroth homology of this complex, but it has extra data. Okay, like a basic classical. As when you had said, like there's a sense in which you could say, well, no, these should already be derived sections already, and think that that's will be. Okay, so let me do examples really quick. So you have the constant sheaf. Let's say K is a field, so constant sheaf F equals K. Sometimes it's denoted like K sub M if you're in a manifold M. In our case, M is R2. So that's a sheaf that literally for every open set assigns a constant vector space, and then you have an empty map all in between. Then it's global sections. So gamma of R2, this particular constant sheaf. If M is the constant sheaf on the 2, that is just the homology of R2 or the check the code. So let me write these like singular cochains. R2, single. And when I write equality, I always mean like quasi as a chain from without it. So singular cochains. Okay. I know this is trivial for R2, but for a manifold, this is going to be like something interesting. Okay, so if we're computing just the constant sheaf in the circle, then you would have something interesting. H1 when you compute the homology. Okay, questions? This is as far as I'm going to try to have any theory introduced to. The rest are going to be like really practical examples. Okay with that? All right, so this is a constant sheaf. That's an example of a sheaf. There are many operations that you can do with sheaves, and now I want to give you some examples of sheaves in practical real life that you can use. And the ones that we're going to use for Legendrians are slight enhancements of these versions, but they don't go far beyond. So The first example beyond the constant sheaf in there is the following. So example. Doing here, like let J be the inclusion of an open set, sorry, a closed set. So this is a closed inclusion. Say with a smooth boundary. If I don't say anything, it's always with smooth boundary. So what this guy looks like, it's something like that. I mean, it didn't have to be contractible, but this is some set here. See? And the idea is sort of very back to, you know, when in high school or whatever, you learned about like characteristic test functions, like it's one inside of the set, zero outside. So you can replicate that with sheaves. Now the advantage of sheaves is that sheaves do talk to one another. There's on between them, so it's not just like test functions. So there's a lot of rich geometry there. But what you would do is you would take the constant sheaf K on Z, and then you could push forward it, and I'll tell you what it is right now, J lower star of KZ, and that would be a sheaf 1 R2. Oh, that's why I left this here. So a general construction in here is that of the push forward, which is going to be useful, and says if I have a continuous map between two topological spaces. In our cases, these are going to be inclusions of open sets, of closed sets, and you have a sheaf F on X, then you can construct a sheaf on Y, essentially because these being continuous, it will not any open set, the image is going to be open. So F knows what to assign to something open in X. So then in order to assign something open in Y, I take the preimage, that's open again, so then F lower star of F, it's something that is an open set of V, so V is open in Y. You just declare this to be F, whatever you assigned, F inverse of V. And again, for experts, really take everything derived, otherwise, just take sections. And otherwise, it's construction. So when you apply this construction to an inclusion, what is this guy? So for an inclusion, so if F is inclusion, what is the preimage under an inclusion? Yeah, it's an intersection. So then the preimage is intersecting with X. Okay. For instance, that means that if I have an open set in R2, which is far away from my Z, what do I assign here? Well, 0. It's like the empty set, so I get nothing. Whereas if I have somebody that is in Z, I intersect and I assign whatever the constant sheaf weight, which is constant. So the intuition is that this sheaf will look like K, the constant sheaf inside of Z, and then 0 outside of that. Does that make sense? If you're familiar with the notion of a stock, that's great. Otherwise, there's a sense in which you can assign something to a point, which is you take open sets containing that point, you take the co-limit under those open sets given by inclusion, and that's going to define an object, which is sort of what the sheaf assigns to the point. The sheaf doesn't know what to assign to a closed set, but if you take a limit of open sets smaller, you might know what to assign to that. So literally here, the stocks are K inside, 0 outside, and they're K at the boundary in this particular case. Okay. All right. So you have these kind of sheaves, very interesting sheaves. And then in this example, so for this, shouldn't be surprised, the global sections of this sheaf on R2, sheaves now with respect to these, J star K sub Z, that is, well, that's the same thing as singular chains. Okay. So that's like a very convenient way. I mean, probably grad students don't like this if they haven't gone through hatchet yet, but it's a very quick way of saying this is how you recover the cohomology of a closed set. That you just take the sheaf, the constant sheaf, restrict to it, extension by 0. In this case, you get that. Okay. It's a very, very important first type of sheaf we'll study. Are okay with happy with that? Okay. So now, what should I do once I've done the closed case? The open case. Okay. So now I take I an open inclusion. R2 in this case. Open inclusion. Now you could do exactly the same thing. You could say, well, I'll take U in here, and I want something that's like K inside of U and 0 outside. the subtlety here is that if you did something like that, like I star, then you would not get 0 at the boundary. And maybe you really want a test function, which is 1 inside, the stock should be exactly k inside and 0 outside. So then there's a variation, which is something called J lower Schrick, exceptional direct image of K of U. That is a sheaf in R2 with the property, which is the property that we want. So which is kind of 0 outside and K inside. And in particular, I'm saying for this exceptional image, this stock at the boundary points is 0. So how do you define the exceptional image in this case? The exceptional image is defined exactly like this one, except that here, when you take sections, you always ask them to have compact support. So it's exactly the same, except here you say sections with compact support. Okay. And so you're going to get this thing, and maybe not surprisingly, given how it is defined, for this, if you compute the cohomology of the sheaf, the sections, the cohomology for the I, I Schrick, this one, that is going to be compactly supported things. Okay, this cohomology with compact supports. So you recover standard cohomology, you recover cohomology with compact supports, which you can often write in compute as a relative cohomology. Okay, are we okay so far with these examples? So, okay, what is the intuition here? What's going on? Where's the Legendre? That's how I feel when I go to this kind of thing. Where's my Legendre? Okay, don't worry. So, the intuition is as follows. The intuition is, here I have my sheaf in R2, Q1, and Q2. And what did I tell you in the first talk? Well, we said that if you have a curve, in particular an embedded curve, that should lift to Legendre. So if this curve is co-oriented, then it's uniquely going to lift to Legendre. The intuition is that this guy is going to give you a Legendrian which is co-oriented inwards, whereas this guy is going to be a Legendrian which is co-oriented outwards. And I always mix these two up, and I need to compute carefully, but I think I got it right. No. So the idea is that this kind of sheaf, which is constant in here, K, think of it as like characteristic function 1, and outside 0, that exactly is the one that's representing for you this Legendrian knot in here. This Legendrian, this is very, very cartoonish, but this kind of sheaf F is going to represent a Legendrian in some sense in here, inside of the unit cotangent one, the infinity of R2. And this is sheaf impotence. Okay. Furthermore, and in this case, this is precise. In general, it's much more subtle. The idea is that it not only does represent a Legendrian, but it kind of comes with a filling too. And the intuition is you could have coned this entire thing on each cotangent fiber, and now you would have this guy sort of as a cylinder like that. And the filling would be whatever is here in the 0 section, which is Lagrangian, the cone, which is also Lagrangian, and then that's the part that goes south typically, but here you could kind of smooth a little bit, and that's the way you would fill the Legendre. Again, in this case, this can be made precise. For more wild sheaves, it's not true that you can just smooth it into a better fill. Okay, so the intuition is this one. For closed ones, one orientation. For open one, the other orientation. Okay, so now let's do a real life example. So say I want a sheaf that in some way it's trying to capture this Legendrian. Well, suppose, are we happy with this Legendrian? This is the unknown, lecture 1, some Legendrian. But again, think of it in R2, this is where the front is. And now I'm going to choose the set Q, which contains the upper boundary. So let's call these like partial plus Q, and it's partial minus. So this Q contains the upper boundary, but it does not contain the lower boundary. Why am I doing that? Because if I now constrain, so I have inclusion of this Q. Let me just call it F because it's neither open nor closed. But I have the inclusion of this Q inside of R2. Then you can consider F Schrick of the constant sheaf in Q, and that represents, intuitively, it represents this lambda. So it represents the Legendrian associated with lambda or this front. Does that make sense? So this is a sheaf that would be kind of constant here, k, 0 outside, these talks will be k, these talks will be 0. And that's the one that, we'll make it precise in the next board, what it means to represent, but that is the intuition. Are we okay so far?
What's the difference between the upper and lower? Why leave one out and put one in and the
So-
boundary plus and boundary minus? What if I switched the dots and,
You just get the Legendre corriented the other way.
uh-huh.
Yeah, so yeah, if you did, it's perfectly fine. So if you did this one, you would get this one.
Mm.
Which is isotopic to this one, I mean, in this case, but in general.
Yeah.
That's why you gotta be careful. That's why I did these two kinds of separate ways, like this is really with the inner orientation, this is with the outer orientation.
Mm.
And what I'm saying is in real life, you mix both of them. Sometimes you include the boundary, sometimes you don't include the boundary. Are you up so far? Okay, so now the general picture kind of starts to look something like that. So you have a more wild node, like maybe like this one, and then you have something which is like, oh, let me consider sheaf, which is like 4q1. By that I mean put the right orientations, put the right opens and close things. I have a sheaf for q1, and then I have another sheaf for q2. And what I'm telling you is that now you can do something to these two sheaves, put them together in some way that maybe what you get is this sheaf in here. Maybe you're, optimistic and say, well, I just take the direct sum of sheaves. Why not? Yeah, you can do that. You can take direct sums. Think about it a bit more. There's not just direct sums, it's like extensions. And this is the kind of phenomenon you will get. The sheaves can be more complicated, like here. You can have a sheaf like Q2 that kind of passes by here. There's Q1. People familiar with rulings should be very happy about this. So think of this kind of sheaves as being associated to rulings in that sense. Yeah.
Maybe you could go why from perspective of sheaves to what cusps
We want what?
cusps.
We want them?
Don't we? No, if we want to represent them.
Okay, the question is, why do we want cusps if we want to represent an unknot? What do you mean by that?
Well, I mean, you could draw a picture without cusps.
Yeah. You can do that, yeah. So yeah, I mean, absolutely, like, you can take this example from the first lecture. And consider the sheaf which is k inside and 0 outside, and that's a sheaf realizing that Legendre. I just thought, I don't know, I don't care for any. This is the fiber in the infinity of R2, and this is an unknot in a third wall. But you don't have to have cusps. I mean, okay, the way I would think about it, or the way I'm thinking about it is, the Legendrian is the thing. That's the important thing. You are studying it. You draw front for it, and now you try to build a sheaf using the front in a way that it indeed represents the Legendre. And now I'm going to be precise about what I mean by represent. Okay.
I don't know, maybe, or my interpretation questions, like, what if you draw that thing without cusp, but it still has like upper edge, like, which is solid and like a lower dotted edge?
Yeah, you're gonna, yeah, so for instance, here's a slightly easier example. What is the sheaf that represents this thing? It's like a sheaf which is a skyscraper. There's like k in this point and 0 everywhere else. And now you can do like more complicated things. For instance, you can do it like this and then dots like that. But now you're gonna have to be able to switch from an orientation from outside to inside. And now you got a choice. So here you need to decide whether you're gonna use your hairs to go, say, this way. And then it will be this Legendrian, and then you go a bit on the fiber, and then you continue on the other Legendrian. Yeah, I was just trying to keep it simple, but yeah, you're absolutely welcome to, like, every time you hit any point, move on the fiber for a while, which means adding hairs and then continue somewhere else.
Can you express f in terms of I and j?
Can I express f? Any f?
Just this f, like, because this set is going to be like the intersection of an open set with a closed set.
Yeah.
So f should be like I lower shriek with j lower like push forward or something like that.
Well, let's just leave it as it is, no?
Okay.
I mean, it's a perfectly fine thing to say that this is an inclusion of this set, right?
Yeah.
And then I can take f shriek.
Oh, okay.
Yeah, it's like I never needed to, yeah, I just need the continuous one. Okay, so now how does one go rigorously from talking about sheaves like that to saying, oh, this is what it means for the sheaf to connect to the Legendrian? And the notion that's important here is the notion of singular support, also known as micro support. there's a beautiful story about how this came to be. It started with Mikio Sato, and then kind of went down to Kashiwara and Shapira, and it kind of has evolved a bit during the decades. But at least in the context of shift theory, it is exactly the way you link to Legendres and Lagrangians. For anybody who gets a kick out of learning PDEs, if you read Hormander's book on linear differential operators, like Fourier integral operators and such, Hormander did exactly the C-infinity version of all of this. This is an analytic version, and it's very beautiful to work through that book with that sort of Lagrangian perspective, and many of the things are identical. And then suddenly there's one example that makes it very, very different. But it's very interesting. What happened is that Sato visited Weil at the IAS, and Hormander was hanging about. And then Sato tried to explain to, everything is just written. The Sato tried to explain to Weil his ideas about how to use macro-local shift theory in order to define boundary values of holomorphic functions. And then essentially Hormander said, I can do all that like in the infinity setting, kind of much neater, the notion of wavefront to propagate singularities of PDEs. And that's kind of what stuck for the rest of the community. And Sato's idea took a bit longer to develop. But Kashiwara and Shapira did, and by now it's pretty standard. Okay, so let me define this idea. So the first definition that we have to have is the definition of a microstock. Microstock is a generalization of a stock. So what was the stock? Well, the stock of a sheaf at a point is you take little open subsets, smaller and smaller and smaller, and you take the co-limit of that, and you look at what that co-limit is of all the sections by contain. The idea of the microstock, and here it illustrates very well what it means for micro, it's the data of the manifold of M plus a first derivative. And again, this description that I gave in the first talk, that appropriately understood, conduct and symbolic topology is the study of functions and their first derivatives. And here we see this very clearly. When people talk about micro-local analysis, they mean I want to study the function and their first derivatives. PDEs, like first order PDEs, linear PDEs, so on and so on. So what is the microstock? It's a generalization of the stock where now you not only have the data of the point, you're going to have the data of the point and a direction of the point. And you not just care about the sections of open sets as they close up to the point, but you also care about sections in that direction. So this is the definition. So given a point x psi, sorry that the psi is repeated, but it's pretty standard notation. So in R2, and a function f, in this case it's R2, in general it's a manifold M, which realizes that conormal direction as its derivative. So E of f at x psi. The microstock is usually defined mu sub x psi of a sheaf f. It's the following measurement. So intuitively, you have your point x in here, and you can have an open ball u. And now you compute sections. Now, if you're given the open ball and a direction, so that's x, and you have a, every time I say that direction, I mean co-direction. A co-direction like that, psi, you can now, so this defines a hyperplane, that would be the hyperplane here, choose a function, these all defined for terms, choose a function whose level set is exactly like that, so that would illustrate the fact that d of f is exactly parallel to psi, they're in the same direction. And now what you're going to do is you're going to restrict your sections from U to this part of the open set. So to this part over.
Wait, so what's that part? Does it include?
Yeah, so I mean, I'll yes.
Okay.
So let me be super precise. So this setting here is f less equal than 0. So if you have the hypothesis, say f of x is. So say you set it 0, you take the level set that passes exactly to that point, and now you look exactly before. Okay. So now there is a restriction map from this open subset, when I take global sections. So I take gamma of this sheaf assigned to that for my sheaf f, and it maps into gamma for this open set also from this sheaf. Okay, so again, just think, this is what the sheaf assigns to this open set, again, in a direct way, but for something contractible, it's this thing. And now this is what it assigns exactly before where we're using this direction in there. The intuition is that we want to capture moments where this restriction is not an isomorphism. So the idea comes classically from propagation, which is suppose I have a section defined on this open set. And this kind of thing from PDEs, but in your solution, you do not know whether you can go past a certain point. And you want to understand if your solution is propagate past a certain point. And so if these were an isomorphism, then it would tell you that for any section that I have in here, there is a way to extend it to another section kind of globally, and now you're kind of past that singular moment that you didn't know about. Okay, so you want this to be an isomorphism in order to capture the idea of sections propagate. Of course, they might propagate in this direction side, but they might not propagate in some other direction. So that might depend on the sheaf itself, on the space itself, so on and so forth. So because you want to make sure that this captures the things that do not propagate, you want to make sure that you want to capture the things where this is not an isomorphism. And what is zero even only if it's an isomorphism? What object associated to a map F is zero, or a cyclic or whatever, even only if F is an iso? Okay, you unearth your homological algebra, and the answer is the cone. Okay, so the cone of this, and let me for now completely ignore the fact that you shifted by some degree, but the cone of this map, that's exactly what's going to be the microstock. So the microstock is the cone of this map. So the microstock is zero if the sections do propagate at that point in that direction. And you hope it captures something non-trivial happening if there's sections that do not propagate. Does that make sense? Let's do examples, a little bit more examples, but for instance, let's take a section here. Well, there's a section that is K inside, right? And then like kind of zero outside. Clearly, where I'm inside here, the sections in an open set here in any direction, it doesn't matter, is the constant sheaf. Nothing is going to change. So the microstock in any point inside is going to be trivial. Same with outside, everything is zero. So the only chance where microstocks might be slightly interesting is like points at the boundary. Okay, and indeed, I'm going to go into more details of that. Okay, so that's the microstock. So that's the first definition in here. Definition number one. And then by definition, very important definition. So by definition, the singular support of a sheaf, S of F, sometimes denoted mu sub sup. Micro, the mu is for micro, su is for support, singular support, the micro support is exactly the set of points in your contact manifold, the T infinity of R2, such that the microstock, oh, maybe I should make it clear. Here there was a choice of F. Let me color code this. There was a choice of F here. So this a priori depends on F. Okay, very clear. So such that the microstock for some function is non-zero. Okay, and this is for some function for some. I'm going to elaborate a bit more on this, but this is the key definition, because now you've connected the topology, the sheaves on the base, to the cotangent bundle, in particular to this T infinity of R. Okay, so now you created a set in T infinity of R2. So if you were kind of in the wavelengths of the first lecture, maybe you can start to wonder, is this set Legendre? Or is this set empty? Or well, what is this set? And the answer will be, in the cases of interest, this set will be a Legendrian, and we say a sheaf represents a lambda if the singular support is exactly that lambda, or at least containing that lambda. Does that make sense? So it is in that sense that this sheaf was representing this lambda. So indeed, let's compute this for a second. Let's take a point at the boundary here. Now I take a point at the boundary and I want to compute global sections in here, right? And if I'm exactly putting myself in the direction of the inside, I can ask, is this direction in the singular support? Well, that's comparing sections on this open set versus sections on this open set in here. Now, the open set in green, that's zero, right? Because the sheaf is outside. Whereas the open set in there, can somebody give me a section in this red open set? Well, it's a function that's like k inside, 1 inside, and then 0 outside. It's a perfectly fine section. Like, don't worry, it's like a discontinuous function. That's perfectly fine. Okay, so the red has a section which is k inside, 0 outside, whereas this one doesn't have, the green one doesn't have. Note that the reverse thing wouldn't work. So if I'm trying to detect, is this in the singular support, I would have to compare sections on this neighborhood, which we know the answer is k, versus functions on this smaller neighborhood, on which the answer is also k. And in fact, the restriction is an isomorphism because the sections in here were exactly k0, and now you're to the k part. Okay, so these you can conclude is in the singular support immediately because there is an f for which this is non-zero. These you cannot conclude is not in the singular support because the definition of singular support is for some f. And every time you define something for some f, you have the challenge that if you want to prove that something is not in the singular support, you would have to prove it for all f's. Does that make sense? So, okay, now I refer you to the notes. So see notes for a second. For the so-called test for singular support. This is a nice proposition from the book of Kashiwar and Shapira that says if f satisfies a certain constraint, which is really easily satisfied in our cases, it's essentially it's graph df, it's transfers to the stratification, to the normal of the stratification. But it's a very easy to verify hypothesis. Under these ones, this being 0 or not is independent of f. So there's a nice class of f's, which we call them like test functions. And for that class of f's, whether this is 0 or not is independent of f. So actually for that one, you do check that a linear function here is a test function. Then you apply the proposition and it tells you that that's 0 for that test function, but in fact that implies that 0 for all. Okay. So in practicality, you do need to use that proposition, but once you use it, well, you're kind of good to go. All right. I think it's a good moment for y'all to ask questions or complain.
So the definition of microstock, presumably you're taking, maybe you said this, but it's not right. You take the subdirected limit of this over possible open sets of
Yeah, sorry. You guys pull in. Use under reverse. Yeah, it's the same definition as in the stock. The stock of a sheaf is the co-limit of f of u under the system, which is u includes the v, so on and so forth. And so you take the co-limit of these for all of these. Yeah, thanks, Larry. Yeah, in practice, if u is small enough and contractible, you just compute for a small enough u. Same way you compute stocks. Because I mean, the directed system is going to be constant starting at some point, so the co-limit is whatever that constant is. Any other questions?
Sorry, so in the definition of single support, do you want to take closure of this set or
Do I want to take what?
closure?
Yeah, I can take closure. Yeah. I mean,
You mean, a priori, is it already closed?
is it?
Is it already?
No. We can take the closure. I mean, again. Oh, again, the notes should have everything in absolute detail. Okay, I mean, yeah, we can discuss many things. Closure of the ship, why is the ship there? There's a lot of things. I mean, Kashiwara Shapira book just sets up the definitions and properties, and it's like, I don't know, hundreds of pages. As I said, you're welcome to read. Sorry. But yeah, closure is a good one. Okay, any other questions? Nope. All right, so with the definition of the microstock and the singular support, we connect to the Legendrians, and we can start naming something that will potentially, and tomorrow we will argue, is an invariant for the Legendrian. So in general, I want you to note that the singular support of a sheaf is not a Legendrian, has no reason to be a Legendrian. For instance, think about the singular support of the sheaf of smooth functions. For any point in any direction, I can build for you a smooth function, which is smooth right before that point and in that direction, and then the partial derivative in that direction blows up, right? Just do it in R. Like it's something that blows up in. Therefore, for the sheaf of smooth functions, any point in any direction is in the singular support because there are sections that do not propagate. So the singular support in the case of the sheaf of smooth functions is the entirety of the infinity of R2. Now, there is an important theorem that says there is a property, a geometric property that does satisfy So there's an important theorem. We're not going to use the theorem, but it's just good for culture. It's Kashawara-Shapiro. Building on work of other people, including Branch. So the singular support of F is evolutive. So it's quasi-tropic, we would say. That's pretty good. That's some geometric constraint happening. This is only true characteristic 0, by the way, but if anybody really wants to do characteristic P, we can talk some other time. But this is quasi-tropic, so there is a constraint. But actually, there's something slightly more useful for us. And in fact, from the following characterization, so the singular support is minimally quasi-tropic, meaning it has the minimal possible dimension, meaning it's Legendrian. So it's Legendrian. Even only if F is constructive. So we'll talk a lot about this tomorrow morning. So tomorrow morning will entirely be about what it is to be a constructible sheaves and how do you compute these sheaves if they're constructible. But this gives you a very precise connection to something that's pretty classical in the theory of sheaves, to Legendrians. Now, what is the intuition for constructible? In here, for now, we're just going to say, as a little peek for tomorrow, is that it's locally constant. It's locally constant on each piece of the front, on each stratum of the front. So for instance, if I had something like this knot in here, okay, the sheaf that I gave you was really silly because it was already kind of K here, and then it was 0 here, 0 there, and K in there. But what I'm saying here is that as a sheaf, when I look at itself along this segment, that is actually the constant sheaf. When I look itself at a point, well, every point, constant sheaf. When I look inside, it is the constant sheaf. And so the general kind of phenomena you're going to have is like that. The sheaves are going to be locally constant, where the open strata are the open sets, and then the one-dimensional strata are the arcs, and the zero-dimensional strata are going to be the crossings and the cusps. Okay? So again, this is what I was trying to say. If you think sheaves like in life, they're pretty wild. But the ones that we need for Legendrians are going to satisfy this very strong condition of being constructible, and not just being constructible, which means locally constant with respect to some stratification, actually constructible with respect to the front. Does that make sense? Okay, so the intuition for here, how is this used? So now the idea of using the singular support is that, as I said, if our given object is a Legendrian lambda, then T infinity of R2 size standard, we can consider the subcategory of sheaves which have singular support exactly on lambda. So the important category here is sheaves sub lambda, in this case of R2. Again, if I don't put coefficients, I just mean mod K, and that is a subcategory of the category of all sheaves in R2. And it is defined by the condition that it's all objects in here such that the singular support of F is included inside of it. Okay. So that at least what it does, like said theoretically, is like given a Legendrian lambda, is my Legendrian in here, it associates to it a certain category. And out of here, you know, you can try to do things with it. You can create a space, you can try to, I don't know, do this gradient group, say something about this category. And tomorrow we'll discuss why this category is invariant. We'll do it very explicitly for knots to the Rademacher moves. And the statement will be that studying this category, not only it helps you sometimes distinguish Legendrian isotopy classes, but it actually informs you a lot about the Lagrangian fillings of the Legendrian lambda itself. The idea will be that a Lagrangian filling will give you an object here, or a family of objects. That's very much in line with what Lenny was explaining, that a Lagrangian gives you an augmentation, the Lagrangian gives you some kind of sheaves. But conversely, I would sort of promote the viewpoint that anybody in here comes from some unobstructed Lagrangian of this lambda. So this sheaf theory should inform you about what kind of geometry you're looking for. Okay, so the only few things are a bit technical, but let me just give me one, I have 1 minute. Okay. So 1 minute for technical things. In all of these, and I'm not gonna write these, you have to write the little C here, which means compact objects. I can tell you a bit more about it, but what it means really in practice is that the stocks of the sheaves are gonna have to be perfect. K modules, so bounded complexes with finite rank in every degree. In general, for the general coefficients, we're gonna be compact objects there. That's some kind of finiteness condition in here, again, kind of technical. And the second thing I didn't do precisely, that I didn't devote a board because I didn't have the time, is why is this a category? In which sense is this a category? Well, ohms in here are defined already by the kind of ohms that you would have in there. So how do you define ohm between two sheaves? So that's my last comment, is that you have two sheaves F and G. Well, for any open set, you can take F of U, you can take G of U, so those are sections. Now, in the category of coefficients, you can take ohm of that, right? So that gives you something. And now what you can do is you can take sections of this sheaf. So now you take gamma of U with respect to this sheaf. So it's a sheaf. And so now you take sections of this ohm sheaf in here, like this is a sheaf, meaning every time, without the use, this will be a sheaf, the internal ohm, and now you take global sections, and that is a vector space. I mean, this is how you would go with these things. But the point is, given two sheaves, they talk to each other by doing that. Okay, this looks like very elaborate and whatnot. Just do it in an example, and you'll see it's nothing you don't know. Say I take a sheaf that is concentrated in this set, F, and a sheaf that is concentrated in this G, like the constant sheaf and the constant sheaf. What is ohm between these two? Well, between here, if I take a point in here, well, F is 0 here, right? So there's no ohms. 0 is the only ohm. If I take a point away from here, there's no ohms here. So what is ohm capturing in all these simple examples? It's capturing the intersection. I mean, it's going to capture the cohomology of the intersection, in this case, just sections of the intersection. So ohms between sheaves are kind of a way to categorize and talk about intersections and many other ways, and the right ways as well. But it's really just doing things. So when you're doing ohms between sheaves in here, for instance, ohms between Q1 and Q2 are just going to be concentrated in these 3 points. And then you can use these ohms in order to construct something. You're going to glue together Q1 and Q2 through these morphisms. Okay. So again, keep in mind the idea of ohms as intersections, and then you can try to start building sheaves. So the exercises in the notes are of this sort. Here's a Legendrian, try to build a sheaf whose singular support is that Legendrian, so on and so forth. Does that make sense? Okay, again, I'm available. Just ask questions anytime. And tomorrow we're going to start by computing very explicitly what it means to be constructible, and then what it means to be in this category, how to take that out of the front. All right? Okay, thank you.